Good morning, dear guests, and welcome to our first, I should say, Quantum4Utilities webinar. We are sitting here. We have the honor and pleasure to sit in the Elia Media Studios, some beautiful studios here in Brussels. And what we are going to do today is to talk, of course, about quantum computing, but more specifically about quantum computing use cases, applications, and projects that have been done and are going on in the utilities and energy sector. So very applicable. I heard this morning that we are more than 170 people that subscribe to this session. So I don't know how many you are in right now, but to us, this already looks like a big success. I have four distinguished expert speakers with me today. So that's already a good thing for me and for you. And before diving into the topics themselves, I have some practical information for you. So first, as I said already from the beginning, and I repeat it a couple of times, if I myself, I go to conferences on quantum, we get these presentations mainly from technology companies on what they are capable doing today already and in the near future for a specific sector. But all these presentations, they say quite on the surface, and that's not what we're going to do today. We're going to be very honest with you, explain what has been done already, what is possible, what is feasible and plausible for the near-end future. Now some practical information first. First of all, this session is recorded already now. So if you need to leave your screen for a couple of minutes, no problem. You will receive the recording after the session. A second thing, and that certainly you are used to, from time to time you will see some QR codes on screen. We want this session to be interactive. Although it's a webinar, we want it to be interactive, so you can ask questions all the time. If you scan with your phone the QR code on screen, the one you see right now, then you will get guided to a Slido application, an application you probably know, and you can drop in questions at any time. We have foreseen fixed moment after each presentation of all speakers, but also at the end, you will see we have a couple of extra Q&A possibilities. So that's some practicalities. For the next thing I will do to you is introduce our four speakers. You will see there are three sitting around the table here, and there's one speaker offside. First of all, Mark Thienpont. He is responsible for quantum. He's a quantum expert, Mark, at Delaware. Delaware is a global consultancy in technology. And Mark has been driving some interesting projects on quantum already, very applicable, and he will explain one of his projects, one from the Water Group, has been done with the Water Group, and the Water Group is a water supply company here in Belgium. Then there's Jose from Elia. He's quantum lead at Elia, and notably from the quantum research team. At Elia, they are doing research profoundly on quantum since a couple of years now, and he wanted to share some insights about the why, what, and how of quantum at Elia with us. Jose is also specialized in AI and mainly AI for operations. And then there's Eric. Eric, many of you probably know, Eric Michiels. He's a quantum technical architect at IBM, I should say. And Erik travels all around the country to give these kinds of sessions, but in settings like conferences and at universities and so on since many years. I think Erik is the most well-known quantum ambassador we have in Belgium. And Erik is also a Qiskit champion. So he will explain a bit more during his presentation what Qiskit is all about and what it can mean for you and for your organization. So that's three speakers. And then there's Giorgio Cortiana. And Giorgio, he's dialing in from Germany. Giorgio is leading the energy intelligence team, I should say, of E.On. And E.On. is, like Elia, an international energy company. And what Giorgio is doing is making sure that, like AI and other advanced technologies, quantum is embedded in the digital transformation strategy of the company globally. And that's what he will talk about, but with, again, very concrete examples. So the promise is that we don't stay just on the surface, but we dive deep into the different to the different topics. And then a last word on practicalities before we kick off. We have divided the webinar into 3 sections. So in the first section, Jose will explain a little bit what quantum technology and quantum computing is all about, just to make sure that we all get at par, at the same level of understanding. And then he will explain what Elia specifically has been doing so far in the area of quantum. And then he will be challenged by the 3 other speakers, Mark, Eric, and Giorgio, with their specific company-specific and industry-specific use cases and examples and so on. So that's the second part. And then in the third part, we have foreseen 2 extensive Q&As. One about the question, what are the limitations we have today, we face still today regarding quantum? What stops us today to go further, to do more? Because as you will see in the presentations, sometimes our speakers will be very honest and say, this we could do, but this we cannot yet do, and so on. And so this is what we want to overcome then with a second Q&A, and the second Q&A is about the future. What can we all together, we, but also you, I mean, how can we pull you in to go a step further into co-creation and open innovation and make sure that we accomplish what we are striving for? But I'll come back to that at the end. And I think with that, I give the floor to Jose.
Thank you, Jan. Thank you for the introduction. But before beginning, just you forgot to introduce yourself. So Jan Sonck, he's the Quantum Circle Community Manager. Okay. He's the founder of the Belgian Quantum Community Circle and also Quantum Technology Lead at Proximus. Maybe you can give a few words on the Quantum Circle community.
Yeah, I'm so nervous, Jose, that I forgot to introduce myself. I'm sorry. So what's the community about? We set it up with a couple of, I always say, enthusiasts and experts in the beginning of last year. Our community consists today of about 120 organizations. It's all universities, research centers here in Belgium, also companies, technology companies like IBM, or consultancies, end users more and more, and that we're happy to see, and a couple of startups even, and our ambitious, I will come back to those at the end of the presentation, Jose, because I want to leave the floor to you.
Thank you, Jan. Thank you. Then let's begin. I'll have my presentation will be like to see on the surface what is quantum computing and also to show what Elia has done so far. And then I will leave the word to my co-speakers that will go more into detail in many of the topics I will be introducing here. Many times people ask the question, what is quantum computing? And I think an easy way to explain is to compare it with classical computers. Most people know that classical computers are based on bytes that can be either 0 or 1. It's a very mature technology where we have semiconductors that can implement logic gates, and from these logic gates you can do all sorts of computations. You don't need to know electronics. You can use high-level languages that are then translated into computer code, and they are deterministic. On the other side, we have quantum computers. These are based into qubits, which have 2 main properties, is superposition and entanglement. They are probabilistic, and they are different sorts today of quantum computers. It's not a mature technology, so there is not one yet that it's above the others. But what is superposition and entanglement? Well, I said that bits in a classical computer are either 0 or 1. Qubits, they can exist in multiple states at once, not just 0 or 1, but a superposition. Just like the Schrodinger's cat that can be dead and alive at the same time. And then entanglement, this is a bit more tricky, but qubits can get entangled, meaning that you cannot describe qubits apart from other qubits they are entangled with, but they are part of the whole. And if there is something happening to one of these entangled qubits, the same will happen to the other entangled qubits, even if they are far apart in space or in time. And these two are the foundations of quantum computation, because with these two properties, you can create the equivalent of a massive parallel classical computer. When it comes to the technologies of qubits, there are different competing technologies today. You have the superconducting qubits. These are using superconducting circuits to create these qubits. In the trapped ions, they are trapping the charged particles into electromagnetic fields. The spin qubits use the spin properties of particles. Photonic are using photons. This is more used for communication. And the neutron atom qubits are, how to say, capturing atoms with lasers to then do manipulations and use them as qubits. And the most recent one is the topological qubit. This has been announced by Microsoft some weeks ago. It's not yet a mature technology. They have shown it with maybe just one qubit. If you take superconducting or trapped ions, they have already shown that they can scale to more than 100 qubits. That was for the types of qubits, but now in terms of the purpose of the quantum computer, you can distinguish three main types. You have the universal quantum computer. This is the classical version, sorry, the quantum version of classical computers. You can program those. The quantum annealers, these can be used for optimization problems. And then you have the analog quantum simulators. This last type of computer is more used in chemistry and material science and allows to simulate a molecule or a material and see how it would behave. But in our case, for the utilities, today we think that the most interesting one are the universal quantum and the annealers. If we look more into detail into universal quantum, those are very similar to classical computers. You can program them. You have different sort of logical quantum gates in the same way you have gates in classical computers. And these quantum logical gates, they are going to create superposition. They are going to create entanglement between the qubits. And by putting them together, you can create quantum algorithms. The quantum annealers are somehow different. They cannot solve universal problem, but they are specific to optimization problems. They use a property of quantum physics, which is that quantum systems tend to go to the lowest energy state possible. So if you can model an optimization problem as a quantum system, then you can use a quantum annealer. And there is a way of doing that. It's using what is called in mathematics a QUBO formulation for quadratic unconstrained binary optimization. These my colleagues will go more into detail into that. And these quantum annealers, the advantage is that in theory, they should converge faster than classical algorithms, and they should also find the global optimum. While if you work with classical algorithms, they might converge to a smaller or local optimum. Now a bit of computer science theory. I'm very sorry because this is really an overview and it's a very complex topic. But I think that what you have to understand for today's session is that in computer science you have what is called the NP hard problems or expensive problems. This stands for non-deterministic polynomial. Those are problems that for classical computers are not going to scale well, meaning that if you give the same problem but twice as big, it will not take 2 times more to run. It might even be exponential. And you have other spaces, such as a quantum easy or BQP, in which you have some potential speedup. But it's not known yet in computer science how much these two sets overlap. We have some specific examples. You have the most known is Shor's algorithm, which tackles the factorization of integer into primes. This is an NP-hard problem in computer science, in classical computers. But Shor's algorithm allows a significant speedup when you use quantum computers. You have the Deutsch-Jozsa, you have Groover search algorithm. So there are already some examples that have been found in this intersection between the NP-hard and the BQP space. But you need, for every NP-hard problem, you need to do research and find a quantum algorithm. That's the question mark that you see on the screen. And it could even be that for some specific problems, there is no an algorithm, a quantum algorithm with a speedup. And that's the exclamation mark that you see on the screen. Just to say that you hear sometimes that quantum computing is going to speed up everything, is actually focused on very specific problems, and it requires a lot of research in computer science. Now, why invest time now into quantum? We tend to compare it with AI, because AI was also a technology that started a long time ago. In the 50s, all the theory on deep learning started, but we had to wait for the 2010 to have enough data and enough processing power to put all these things into practice. You can say that it took 70 years to AI to have an explosive impact and become something that we use every day now. And why we think with quantum it could be faster? Well, because we have the experience from AI. We have the lessons learned from AI, and we see also a lot of investment now in quantum. We see a lot of interest from the EU, for instance, and we also see that hardware is progressing rapidly. 10 years ago, we had computers with just a few qubits. Today, we've passed the boundary of more than 100 qubits, even more close to 1,000 qubits. Today, we are in the NISQ era, which stands for Noisy Intermediate Scale Quantum Computers. Those are quantum computers. They are still not 100% reliable. There is decoherence and noise on it. They are not big enough to tackle big problems, but with all this together, they are still useful to do research and maybe to start to do investigation. So we can expect that maybe in the next 10 years, we could see this industrial deployment, and Eric will show the ambitious plans from IBM later during this webinar. Just to give a brief overview today of the providers out there, we have, when you look at the gate-based or universal quantum computer, we have IBM and Google offering computers based on superconducting qubits. With trapped ion, we have IonQ and Honeywell. With photonic, it's Xanadu and PsiQuantum. And with topological, it's Microsoft. It's here in the slide, although as of today, they are not offering these topological qubits as other providers are doing. There is no offering from Microsoft in that sense. And in terms of quantum annealers, the most known one today, and which is open to everyone for use, is D-Wave. And we have to be careful because these different providers, sometimes they claim supremacy, quantum supremacy. They say that they have been able to run an algorithm much faster than a classical computer. It's true, but these algorithms they are testing, they might be of no interest for everyday life problem. Of course, it's interest for computer science research, but as of today, there is no supremacy when it comes to a useful everyday life problem. So that was a very short overview on quantum computers. Now what I would like to show is the Elia Group quantum journey, the research that we have been doing in the last years. But first we have to see what is Elia Group. So Elia Group is a global energy partner that has several different subsidiaries which operate in different countries. The mission of Elia Group is to make the energy transition happen and work towards the decarbonization of the energy systems. You can see on the left side of the graph, we have what we call the regulated activities. We have Elia Transmission Belgium. This is the TSO for Belgium. We have the equivalent in the north and east of Germany with 50 hertz. And we have NemoLink, which is owned partially by Elia Transmission Belgium, which is an interconnector linking the grid in Great Britain to the Belgian grid. And then this knowledge that we have from the regulated activities is harnessed to operate in the non-regulated subsidiaries, such as Elia Grid International, which is an engineering consultancy company. We have WindGrid, which is offering offshore solutions around the globe. And we have Rialto, which is a European marketplace for data and energy services. If we focus on the regulated activities, the responsibility of Elia Transmission Belgium and 50 Hertz, both for Belgium and the north and east part of Germany respectively, is to bring the electricity which is produced to where it is consumed. So it means that they have the ultimate responsibility to operate the grid round the clock, meaning that they have at all moments, they have to match the production and the consumption round the clock. They have four different, they have three main tasks: is to maintain the grid, to operate the grid, and for that to be done, they have also to facilitate the market and to make it even for every partner that would like to join the energy market. In order to have the grid operating in stability, there is one of the main problems is congestion management. We need every day or even every hour to reconfigure the grid in order to take these flows from the production side to the consumption side. From a mathematical point of view, it's a highly complex optimization problem. It has also enormous impact in terms of cost, because if we need to take real-time actions, what we call redispatch, we need to lower the production somewhere, and we need to increase the production somewhere else, which has an enormous cost for the society. So this is a crucial cornerstone for grid stability for TSOs. What happens today is highly complex, as I said before. We have time constraints because we cannot wait 4 hours for this to run, but it's actually taking hours. We would like it to be faster, and for that to be done, we are reducing the problem, meaning that we are making some hypotheses, we are making some simplifications, but this means that we are getting far from the optimal solution, and this results into higher redispatch costs. So this was a good candidate to test on Quantum and see if we could do some speed up in Quantum. And why now? Well, because it's not going to get any better. We already today we have challenges to do the grid optimization. We have a significant share of renewable in the grid, but this will not get any better because we will get more renewable into the grid with more volatility. We will get also more PV, we'll get more electrical cars, adding also more volatility to the demand. And this means that we will, in theory, we would like to run this algorithm as often as possible to have an optimum operation of the grid. So we wanted to test this on Quantum, and we knew from the beginning that we could not throw the whole grid of Elia into a quantum computer because they are not big enough yet. We started with a simple congestion management problem. And then we did the same track we do for the classical solving. We formulated it as a MILP for mixed integer linear program, meaning that we want to find in this space that you see on this graph, this geometrical space, we need to find the combination of variables, which are the production of the power plants, the configurations of the transformers, which configuration allows to reduce the overall cost of operation of the grid. And then in order to use it in Quantum, we needed to translate it into a Cubo, as said before. And for that, there are different libraries. If you use Qiskit from IBM, you have the possibility to formulate a Cubo. And D-Wave is also offering the Ocean library that allows you to go from a MILP or other formulations into a Cubo. Then when we had our Cubo, which was relatively small with 127 variables, we dropped it into Gurobi. Why Gurobi? It's a classical solver that we use today, but we wanted to see if the answer we obtained from the Cubo was the same we obtained from the MILP. This was the case, meaning that we get some, we didn't change the semantic of the problem. And then we tried on IonQ. This was not possible because we didn't have enough qubits. And we tried with Microsoft quantum-inspired solvers and with the D-Wave quantum annealer. In that sense, we managed to run the Cubo on those computers, but when we look closely at those, the solution that we got was outside of this acceptable space. It was outside of this geometrical space, meaning that it made no sense to take such a solution. We wanted to understand why, and for that, D-Wave offers the problem inspector. This allows you to see the Cubo formulation on the left in a logical way, and then how it is mapped to the hardware on the right. And what we realize is that the formulation that we have, even if it's 127 qubits, and D-Wave has 5,000, actually the connectivity or the level of entanglement that we had in our Cubo was too high for the level of connectivity that you have in the hardware. D-Wave offers today connectivity between 20 qubits. We needed 80 or more. So in D-Wave, they try to map logical qubits into several physical qubits, but because of the noise and decoherence, then the answer that resulted out of it was meaningless. So that was a bit the conclusion of our journey. We see that it's not straightforward to use quantum computers today. Even if you go for universal or annealers, you need to do some algorithmics or you need to do some reformulation. But we see that the hardware is evolving very fast. We will see from different providers what's the roadmap. And we also realize that we need active research in fields which are a bit outside of what we are used to do in Elia. We need research in algorithms, in mathematics, and not just in the business knowledge that we have.
Okay, are you finished, Jose?
I'm done. Yeah, thank you.
You're finished. Ah, okay. Because I had this question on my mind since I must say half of your presentation. Because thank you, you gave us a very good overview of quantum. I would say a 5-minute tutorial in quantum computing, and then of course you explained very well the journey you have been going to so far. But what I was reflecting on at the end is that there is still a lot of work to do. but we'll come back on that one. There's one thing that ticked to me, and that was you mentioned a couple of times supremacy, and that at this stage, or even in the short term, supremacy will be limited to a narrow set of cases. Can you say something about where do you see that quantum supremacy can become useful for the energy sector specifically for your kind of cases?
Yeah, sure. Because it's true that we mentioned that not all problems can be solved with quantum, but it's not how many problems you can solve with quantum. It's more the impact of those problems. And if you look, for instance, at congestion management, the difference between having a good enough solution from classical computer to have the best solution, it can have a huge impact in terms of cost for the society. So in that sense, it's worth investing because the outcome of it can have a significant impact for society.
Yeah, that's a nice one, and you explained this a couple of times when we not only prepped this session, but when we met the first time. I was astonished by the potential impact for society, but also on sustainable production and greener consumption that quantum might have if we do the job right, if we manage to do the job. But in order to do that, we'll dive deeper now into 3 use cases. If, dear guests, you have questions, put them on Slido. We come back and we give Jose the chance to answer your questions more at the end of this session. But first, we go into what we call the second part of the session, into the 3 use cases. And I'll start with Giorgio, because I'm convinced, Giorgio, that you will dive even deeper with us in the specifics of grid balancing and certainly for energy, isn't it?
Yes, thank you for having me. It's my pleasure to provide you with a bit of a high-level view of what we have been doing at E.On so far to explore and unleash the power of quantum computing for the energy transition. So if you can move on the next slides, let me just quickly introduce E.On. E.On is a utility sector that is serving 47 million customers and managing 1.6 millions of kilometers of grid within Europe. And we are connecting also 1.7 million renewable energy assets. So as we already understood from Jose's presentation, it's actually pretty complex to manage the current energy systems. And what you see in the video that I brought with me is a little bit of a snapshot of how volatile and dynamic are energy systems when it comes to renewable infeed and energy demand. So you see in red the demand aggregated over zip code levels in the north part of Germany. And in yellow, you see the corresponding infeed that we get. And every frame of this picture is basically a 15 minutes interval over a couple of days after Easter 2024. And you can imagine that this dynamicity is not just limited at the zip code level, but if you go to the next slide, you should actually imagine that to be actually going through the capillarity of the network, so the previous one, and actually serves go down basically to the lower level of the low voltage grids where you have the households at the end that are connected. And here you see in the small graph an example where you have in yellow some potential households which are equipped with PV, which potentially can feed into the grids and serve basically other consumers that are highlighted in red. And this, as I said, is happening. Actually, was a picture from last year. And if we prospect how things will change, I took the example for Germany. So in the next slides, I provide you with a view of how the energy system is going to develop relative to 2021 for the case of Germany. And as we know, consumption is actually going to increase due to the electrification of different sectors by a factor of 3. And although it might not be sounding like a big number, you have to consider that we have to adapt basically the energy system for this 3-fold increase of demand in only 20 years. And if you consider that and you put in perspective how long it took to build the current energy system, which was about 100 years, it seems to be still already a big challenge. At the same time, we see that renewable energy generation will increase by a factor of 8 or 4, depending on whether you took into consideration PV parks or wind parks. But what is even more astonishing, if you move to the middle of these slides, is that we'll have bigger increase in the number of appliance and actors that we'll see in the energy sector. So for example, we'll have a 14-fold increase of the heat pumps that we have in the systems, at 31-fold increase in the number of vehicles that will be around. And of course, we will have also a much larger increase in the power to gas and electrolyzer capacity installed. And if you move again, one particular important topic is actually the storage and flexibilities. So we know that electricity is hard to be stored, but we can use PV and battery system as well as stationary batteries to supplement the energy at times where, for example, there is no wind or no sun. And there you see that the number of actors and the capacities that are involved will be increased basically 100 times. And that's basically setting the scene. So what are the key to success to master this increase and the pace of change in the energy systems? We see three main pillars. So if you move to the next slides, the first, of course, is to invest in the physical infrastructures, meaning that we can make it digital. We should reinforce and extend it and allow more integration of renewables. And at the same time, through digitalization, we want to allow to make these infrastructures smarter and self-healing with a number of automations of processes that have to do with the monitor and control of the system. What is also important is also to find ways to orchestrate optimally the energy systems by allowing either individual or collective flexibility and demand response services to basically shape the demand curve toward those that we see are the productions of renewable infeed. And in this case, of course, we are all with full power into the digitalization and AI. And if we move to the next slides, we see actually quantum as an additional and complementary technological enabler, basically adding to the standard technological stack of CPU, GPUs, and TPUs. And at E.On, we are actually looking at the three main pillars where quantum could be of providing an edge. The first one is similar to what Jose already spoke about, is in the area of combinatorial optimizations, but we are also looking at quantum computing to enhance the AI and machine model that we are already using in the systems. And finally, last but not least, we see a potential of quantum to speed up the way we can analyze and do scenario modeling. I brought with me three use cases each, and I hope with that we can provide you a little bit of more tangible insights on what we are doing. So if we move to the next slides, one of the things that is important to master, right, the complexity and allow the energy transition is to have a decentralized energy system optimization. And the idea here is that you can actually group consumers and customers together so to allow the more self-sufficient and dynamic energy community. And the idea is that to identify those communities or coalition that match local prosumer and consumer to boost basically the locally produced green energy and thereby helping balancing the power grid. So if you can produce and use the electricity locally, you don't need to transmit it and transport it elsewhere. This is a problem that is pretty easy to say. For example, if you look on the top right plot, this is a view of a zip code in Munich. And you can imagine that you want to group basically customer together, and you can do it basically based on proximity or other measures. And if you look on the bottom part, so the bubble on the left, basically we see this plot that we saw already before, where we have actually in red some productions units that are proposed to inject energy into the grid, and then we have some consumptions that are shown in yellow, in blue. So what you want to do by this grouping is to group together these prosumer and consumers, such that as you see in the color on the second bubble from the left, so that the local energy demand that is shown on the right-hand side bubble is actually minimized. So you consume as much as electricity that is produced locally. And this is a problem that is hard easy to say, but a bit harder to realize. And this is explained in the plot on the right-hand side, where we have the runtime to basically solve this optimization problem as a function of the actors or the prosumer that include into the into your configuration. And what you can see is the light blue curve, which is the classical solutions that you see experiment basically an exponential blow up in terms of runtime. And we compare with some solutions which are actually based on the annealers, as you see down here in D waves, and also with IBM Quantum. What we see here, you can of course also have way more information by looking at the plots, is that quantum computers may offer much better scaling than the classical one, although as you see the scale of the problem that we are use is not yet at the zip code level, but is only a few hundreds of prosumers. So if we move to the next slides, I want just to introduce how we are actually looking at quantum computer to help us managing, for example, the e-mobility case of vehicle-to-grid scheduling. Again, the problem at hand is you have a fleet of EV vehicle, as you see in the chart in the top left, and you want to determine as a function of time how much charging capacity you want to allocate to each. The difficulties is that, of course, EV vehicles are typically not fixed and they move around, they might not be available, and you see this discontinuity in the plot. So you basically have to understand how many vehicles you have available, what are the charging needs, and of course, add a number of constraints that can be, of course, the desired state of charge after a given time, as well as some site limitation in terms of grid connection. And depending on the number of units and the complexity of the constraints, the time to solution can actually grow beyond practicality, because you need to make sure that you can activate or market the flexibilities or procure the energy from your customers. What we did this, and it's actually a very complex combinatorial optimization problem, we actually turned it to in a new approach, and we actually develop it into a machine learning ones, basically offsetting the harder part of the optimization problems into a learning of models that basically decides based on the situation what is the next best actions. And what turns out to be the result is shown on the right-hand side, where you see again the solver time, runtime as a function of the number of vehicles, and you see in purple what is actually the approximate dynamic programming, the classical solution, and you see that the solution explodes over as a function of the size of the problem that you see, and then you see how much favorable scaling we do have for this machine learning approach. As you see the classical one in green, and then in orange one the for the quantum version of it. And again, I put here the links that you can see for that you can use to get further details into that. Last but not least, I want also to provide you a case that we did for scenarios modeling, and in particular for the energy portfolio weather risk analysis. As a company, as an utility, we are supposed to provide the energy to our customers, and of course to make sure that we procure the energy upfront. The idea is, for example, if you consider gas, is that the consumption may vary according to the weather situations. And this is shown, for example, in the map here. That might be a storm in Sweden, or it might be super sunny in Italy. And this, of course, change the energy demands and based with respect to what we forecasted. And of course, depending on the outcome, for example, if you have a colder or warmer winter than anticipated, and you have some fluctuation in the energy price, this can create some exposure of E.On, some financial exposure and variation of the P&L. And of course, to study this, you need to involve a large number of Monte Carlo simulation or scenario, where you take into account the number of the locations, the type of contract that you have with your customer, the horizon that you want to use for the optimization, as well as the number of price and weather variations. And this is not only critical for the E.On business, but also important to secure affordable energy costs to our customers. And this type of evaluations, so the portfolio energy risks, are done typically overnight. But what if we could do it and have a quantum speed up? Well, of course, we could go more close to real-time planning and decisioning, and have more frequent reassessment of the portfolio risk, enabling the mitigation measurement to be implemented straight away. And the idea is that actually we look at this to quantum computing, and we develop jointly with IBM a novel algorithm which have a proven quadratical speed up with respect to the current classical ones. Of course, this is it looks very good. However, due to the depth of the algorithm, this is actually an algorithm that we suited for fault-tolerant machines. That's basically the three use cases that I wanted to provide to you. Let me just close with the next slide. So as Playmaker, we are really leading the way in innovative and sustainable digital solutions to help and transform the way Europe is power for all. And our ambition is actually to explore, but also unleash as soon as possible the power of quantum computing to drive business value and boost the transition, so through green energy. Thank you very much.
Thanks, Giorgio. Thanks a lot for taking us deeper, I would say, into, on one hand, the challenges, but also the solutions linked to the complexity of grid balancing, seen with the, if we look at the explosion, I would say, not fast growing, but explosion on the one side of production elements, sources like renewables, but also on the consumption side, like electrical vehicles and heat pumps and so on. I'm sure that mathematicians and data scientists on call, they are already heating up their brains to see how they can jump in. That's at least what I hope. But first, maybe I see that there's some questions already from the audience. Jose, can you?
Yeah, sure. We have a first question, which is, if the advantages of quantum computing haven't yet been clearly demonstrated for optimizing the energy grid, are we betting on a speculative future rather than a practical present?
Yeah, I think this is a pretty interesting question. On the one hand, we know we have seen before, right, that the hardware progress is accelerating. At the same time, we also know that the problem size that we see in the practical application, the energy system, are already still too big to be solved into the current machines. However, I think it's important to note that you need to prepare, right, to be able to leverage quantum future and the future machines. It's not just that you wait and sit for quantum computer to become big enough and law is free to be able to tackle your problem. There is a lot that you can do from the algorithm side in order to make your algorithm fitter for the current hardware. So you can design your algorithm such that you need less qubits or less gates by achieving the same thing. So I think the key to success here is really to chain together and leverage the hardware progress as well as working hard on the algorithm development so that you can get earlier advantage out of the current machines. And that's actually why we are looking into that at the moment. So we are preparing for a practical future.
Do we have time for a second question?
Yeah, I see a second question. If the advantage of quantum computing, how is congestion management a problem that is not easily solvable by traditional digital systems? If a standard state estimation algorithm is applied, energy systems can already be modeled quite accurately. I think I'll take this one because it's related to the use case presented by Elia. It's just, indeed, there are libraries and it's relatively easy to model energy system, but the search space, it's enormous because we need to operate the grid in a safe state, meaning that we are not just doing one simulation to know what's the optimum state of the grid to use today, but we also need to make simulation all the n-1 cases, meaning that we're going to see, will the grid remain stable if we remove one big element, like a big production plant, or a big transformer, or a big tie line, and then also in n-2. So if the grid has to operate in n-1 and also n-1-1. This makes enormous search space, and that's why this can take a lot of time to run.
Last one?
Yeah, how can we rely on quantum hardware for critical infrastructure problem when qubit fidelity is still fundamentally probabilistic and not deterministic?
That's a good
unlike
one.
the physical systems that we are trying to control.
Maybe Eric, is this one for you?
First of all, I think in the formulation of the question, I would say quantum computing is always probabilistic. So still, it means it is probabilistic computing. And Yeah, the rest of the question, yeah, could you please display it again? That's the first thing. And the rest of the question, could you please show it again?
The question was about using quantum computers at this stage in an operational environment. Are we already there? Is that already possible? That was, I think, the question about.
I would answer it as follows. Quantum computing will always be a complement to classical computing. So they will enforce each other, and meaning that there is never a kind of complete risk only by using only quantum computing. So it's always a combination that will be used and even improve the quality of the decision making.
Or can I conclude that you follow a little bit the perspective of Giorgio and Jose, where you say maybe quantum utility, as IBM calls it, quantum computing for everyday use is not already there, but this shouldn't hold us back for starting to explore and experiment, because it will take time to get there, and we better start now to make sure that we. Sure. That's a bit what you want to say, I think.
Yeah, indeed.
Okay.
Indeed.
Okay. Can we close this Q&A then and go to the next speaker? Because I would like, and thank you, Giorgio. I'm not sure if you're still there, but thank you for spending your time with us. Appreciate that a lot, and hope to see you soon.
Thank you for having me.
Next topic has to do with water, Mark. We go from electricity to water, and I hope we will not mix both here at the table. You promised to bring us a use case of the watergroep, Mark. Can you?
Well, water distribution networks is indeed something completely different. I think this use case is different in a sense that there was not really a solution how to tackle it. There was no algorithm. It was just not tractable. That's on the contrary of what we've seen before. There was something classically, and we want to speed it up. Here we indeed want to speed it up from completely impossible to something that at least works. So in that sense, this kind of new. Maybe first of all, where is this coming from? I'm working for a company called Delaware. We are providing IT services to businesses and really focused to business processes. So we do not really want to go into like chemical engineering or material science or whatever. It is really the business process optimization in that aspect, or implementing ERP systems. Like 4 years ago, as I have a degree in physics, I got the question from the partners like, hey, there's a lot of fuzz around quantum computing. Maybe there is something that we should know that we can apply towards business processes that has added value versus something that we don't have today. So from that assignment, I started just looking at what is out there in the world that is already working today, not the theory like, okay, in that many years we will have something, or in 2030 there will be something, or what do we have today? And in that aspect, I got into a kind of conversation with the watergroep. We are already working with the watergroep for many years to solve a problem that they have, meaning the distribution of water is confronted with a problem of leakage. And that's one of the, each and every water company has that. You have pipes in the ground, you most of the time don't see them, and if there is a leak, you don't actually know where that leak is. So we got into contact, and they actually were at a very specific location. I'm not allowed to say the name of that location, but they are in the subpart of where they provide water. They were actually doing physical experiments with hydrants opening up, and where do we have to put measurements to be able to see where the hydrant is leaking, and so on and so forth. That was very interesting, and we just proposed, let's combine our forces together and just do the experiment. So that was just what can be learned from this altogether. Some words about leaks. So in water distribution networks, 20% of all the water produced in Europe is not being consumed. And the biggest part of that is, the main cause of that is just leaks. Now imagine that, how much money goes into producing water, cleaning it, and so on and so forth, and distributing that, and then you just let it leak. That's a pity. So the first thing is there a leak inside a part of the network? That is something that we can solve with AI and with data science. We did that already many years ago. But where is the leak? And here I have some images to just give you some idea what could be helpful to detect where the leak is on the left bottom of the page. There is very clear where the leak is. You don't have to be a data scientist to be able to see that. You can just go to that. But most of the time, the leaks are very small or just increasing very, very slowly, and it's more difficult to detect. So at the right side at the top, I found a very nice solution for that. That is actually a real person doing that job at night, because at night there is not much water consumption. It's somewhere in England that this guy is working, and he's just listening to putting his ear to the pipe with that kind of stick and just putting the sound to his ear, and that's the way that he is actually converting towards where the leak might be, basically. That's an approach, and there might be better approaches to that, but that's also an approach. At the right bottom, there's a photograph of two dogs. That's actually in South Africa. They use dogs that are sniffing around and smelling whether there's more humidity in the ground than there used to be before. So they use actually the capabilities of dogs to detect leaks. And you can also use satellites to see humidity increase in certain areas of the country and so on and so forth. So these are all techniques. Actually, what we wanted to do is to have a system in place with pressure sensors at certain locations in your network to detect, just to read out the pressure differences over time, to see, okay, the leak might be there. And it doesn't need to be completely precise, but if there is the right street or the right vicinity of the leak, it's already helping, because otherwise you can just start searching around. Now, this appears to be a very complex problem. When I first started talking with the water group, it was like, okay, we are going to do this experiment. Okay, how many sensors do you want to put in that network? They said 40. Okay, and why do you decide for 40? Well, we have budget for 40, and that was the only lead that they had. They didn't have any guideline. And where do you want to put them? Well, actually, we don't know. We just evenly spread them throughout the geography of that area. So we took contract to KWR. KWR is a consulting company specialized in water. So purification of water, measuring of water, leakages also, those kind of stuff. And we asked the same question, and actually they said, we don't have an algorithm to start computing that. It just takes too much time for it to convert. So we don't have actually a solution. If you look in articles and so on in literature, you find many ideas, but not really a very good solution at converting rapidly. So this was a very nice problem to start with. Basically, nobody knows how to start dealing with that. For me, this was an optimization kind of problem. So I was reading about what is available today. While D-Wave was already providing services to the outside world, I could make access to the D-Wave machine via just my computer. Via service. I had 1 free minute still at that moment. So I had 1 minute of quantum computing time per month that I could use. And that was more than enough for my purposes. So what I needed to do is to formulate the problem at hand. So translate that network with its demand, with its topology, and so on and so forth. Translate that to a Kubo formulation. Again, the same wording as Jose was already mentioning. Actually, it was the same time that we started that you started also your exercise. So that's very, very interesting. So, and as soon as you have that Kubo, you can just run it against that D-Wave machine and you get an answer that you have to observe whether it's good or not good. So that was a little bit the approach that we took. So here I just wanted to note down what is a Kubo looking like. First of all, you have to decide what your variables are. That's a very important decision already to take. In this case, this was very simple. The axes are just, these are the junctions of each and every pipe, or a potential location for having a sensor. And it is a 1 if the sensor is there, and it is 0 if the sensor is not there. So capturing that kind of logic and that kind of variables was pretty simple. That was the first step. The second step is we want to minimize the Kubo formulation. You want to describe a Hamiltonian with quadratic formats and so on and so forth. You know, the Q matrix as described above. And you have a few approaches in literature. So the one approach, which I also see in other contexts, is just directly trying to formulate the coefficients, the Q matrix, based on what you know from your problem. And that can be the topology that you translate, or costs related of having a sensor or not a sensor, and so on and so forth. So Speciali written a very nice article. It's a very, very fat one. Very interesting, his approach, and that was actually our starting point. We started there. It did not really work too well, so we decided we need something differently. The problem is basically that you don't know which algorithm is going to be used to detect where the leak is. You only know, here I'm going to put a pressure sensor. So that gives me the idea that maybe we have to use the ideas of Shannon information theory, you know, the godfather of information theory. And maybe we have to look at that. Just make a decision based on information that you could potentially have without really deciding on the algorithm that is going to be used afterwards, the machine learning model, for example. So we started looking into mutual information, feature selection kind of thing. There is a classical approach being described by Santos Ruiz in Spain, who is really doing deep research on that. So we also implemented that one, the classical approach. And then we figured out, hey, there is also a quantum approach concerning mutual information. And maybe we have to compare those two things. So that was actually, in just a couple of days, what we tried to figure out. So we started off with a very simple network. This is the Hanoi network, which is being investigated in lots of papers. So we actually really know very well how the system behaves. And we also know the optimal point, how many sensors you want to put and where you want to put them. So we know the outcome there. Yeah, I could also calculate it exhaustively what the outcome should have been. So there we have some comparison possible. And then we just upscaled. So with a more complex, even more complex, and at the right top, we had actually the network that we wanted to simulate and wanted to decide upon. So we just start small and evolve fast methodology. So what we did, we didn't go to Hanoi and just drill leaks into the network itself. We were not that disruptive. We just simulated the whole idea. So with, I think there are 31 nodes in here. Potentially, we just started simulating a leak at those nodes. So 1 liter per second, 2 liters per second at that node, each and every node with a certain amount of assumptions to be made. And then you can calculate the pressure drop at each node, assuming that you have a leak at some place. So you build up a kind of big data table. Yeah. That's the first step you have to do. It has nothing to do with quantum yet. That's just a preparation step. What you do secondly, how can you now measure if you decide based on that table that you take those 3, for example, those 3 points that you can measure, you can actually train a machine learning model based on, oh, I know where the leak was, and that was the measurement that I could take of that. And then with that machine learning model, you can predict your node, and then you can start comparing, not just comparing whether it's the same or not, but what is the vicinity. We call that the average topological distance. That's a term that you won't find in literature. We just figured that out ourselves, like this could be meaningful, that you have the topology also in place. Okay, so we applied this method towards the exhaustive calculation. So again, nothing to do with quantum here, because the number of combinations is still quite low. If you were assuming 3 sensors out of 31, you get less than 5,000 calculations to be done. So that's pretty easy. And we come to the point, okay, you put them at those locations, 13, 16, 29. That's actually the best average topological distance that you can have if you measure that. If you do that in a real quantum way, and you also use the Santos Ruiz methodology and so on and so forth, the Santos Ruiz, the classical approach, which was actually saying, if I take one, what is the best one to take? Okay, you decide that. And if you then take a second one, you assume that the first one is still relevant. And you just grow that. Yeah. So it's not like, what is the total group that is giving me the most information, but you just scale it up sequentially. That's Santos Ruiz. So Santos Ruiz is the blue line indicating over there. And the red one is actually, and that's very interesting, is actually also the outcome of the best possible combination of 3 for the quantum. So quantum gave me exactly the same result as the exhaustive calculation of everything that we had. And I could already demonstrate that Santos Ruiz is not really doing the same trick. So it's deviating from that. It's also taking a little bit, well, here at the same time, but you will see that how that one will evolve. So that was already very good outcome, giving confidence like, hey, we are onto something here. If you scale that up, so here with Net3, you have you tripled the amount of junctions. You also add some reservoirs towards your network. You see that the exhaustive calculation was not possible anymore. It would take me a week to just calculate everything, so we didn't do that. Santos Ruiz is a little bit more time to simulate the whole thing to come to an end, 7 minutes. The quantum feature selection, however, still took 1 second, just the same as in Hanoi. So just feeding the Kubo formulation towards the D-Wave machine and getting an answer is very stable, less than a second. What you can see here, that's that graph. If you take one sensor, then it's very high, your average topological distance. So that seems to be dropping and leveling off at a certain moment. The moment that it levels off is here, like you have to take 5 sensors. So that gives you a lead, and you also know where to put them. If I confronted that with the business users at the water group, they said, well, actually the outcome is pretty interesting, because at the end of your network, at the extremities, that's where you feel the pressure drop when you have leaks. So it makes sense that like in 3 or 4 occasions, you put them really at the end. They don't need to be there all the time, but that's already giving us an indication that you're onto something once more. Yeah. Scaling it up once more. So here we again triple the complexity, putting some tanks and some valves into place. You have the same response. So it immediately drops, the error that you make immediately drops by increasing the number of sensors, which is logical, but then it flattens out. So here we could say, okay, take 10 and put them at those locations. At this moment, you see that the Santos Ruiz is already taking 15 hours, whereas our approach is taking still the level of minutes. So this is an indication that this is going the right way. And then actually the area that we wanted to simulate, that was based on 5,000 junctions. But that was limited in the possibilities. Where do we have reach to actually put a sensor? So there the water group said we only want to have the locations where there are hydrants that is accessible to us. So we limit the value space to 635 hydrant locations. Yeah, so the Kubo was reduced by that. Anyway, to prepare for everything, the head loss simulation, the pressure drop simulation took 70 hours. So that's 3 days of parallel compute that you need to be able to do that. Santos Ruiz was completely impossible to calculate. It didn't convert at all. Preparing to go for the Kubo formulation took an additional 7 hours. But then to do the feature selection took, again, less than a second. So that was pretty cool. So I simulated a few numbers of sensor kind of thing. And then you see that curve again, it drops off towards 130 sensors spread over, and you see also the extremities coming back. So that was good. And then it levels off. So here the answer was, if you take 40 sensors, if you do that investment, you could as well put 1. Or you really have to go to 130 to do better as a measurability of your topology, basically. So that was very interesting for them to know. 40, they didn't have a guideline, but it would be better to triple that investment anyway. Yeah. So to wrap it up, we provided now an algorithm starting from a known topology, a known demand within that topology, translating that takes you still 3 days to calculate, to do just a simulation of leaks, then to formulate that back towards the Kubo based on that piece of information, and then you can very rapidly do your quantum optimization process for that. So the preparation step is taking 3-4 days, but it's still a lot better than completely impossible. We were thinking at the end of, or we were dreaming about the scenario that we could translate the topology and the demand or approximately towards the problem formulation directly. The problem is there that water distribution networks are non-linear. It's not like energy. Mechanical problem, so it's not that easy to be doing that part. So we didn't tackle that problem, but it already was a real head start or the solution to a certain problem that we could have. One comment on that. Other cases that I dealt with is actually leading back to the same. But by doing that, there are other ideas coming up that businesses didn't think about. That were actually maybe more important to have. This could, for KWR, for example, gave lead to suppose that we would plant a new part of a city, do city planning. What would be the best measurable topology to be doing? Or do I add a pipe here? What would be the measurability improvement? Right now they can't calculate, but with that, maybe in minutes or hours, they could actually simulate that. And that's could be a new business process overall. That was my story.
Wow, Mark. I'm really impressed because I did promise our guests in the beginning of the session that we would go deep, but you really gave us very deep insights on what you have been doing with the projects. I think we cannot go better than this. It really delves very very concretely into the challenges you had. You took them along, and what is similar with the other cases, you took very well into account the limitations also of the quantum computer as we have them today, and what you can already do with quantum today. And that's a bit a red line I see in all presentations, and also so something that made me tick in your presentation is the 20%. Of course, I knew the figure, and I know in many countries it's even much more. And then I think about countries where water is even more scarce and more expensive than here in the Western world. Yeah, if we could find a solution based on quantum for the problem as you stated it would be a great thing for the world as a whole. Wow, I'm really impressed. And I don't know about our guests or viewers here, but I see that on the Slido there is a question.
Yes, we have a question, which is, if the advantage of quantum computing haven't yet been clearly demonstrated for optimizing the energy grid, are we betting on a speculative future rather than a practical present?
Well, maybe two answers to that. I think I've shown that quantum could have added value for solving an unsolvable problem to get something that is running for days, but still had the option to proceed on that. The biggest complexity I had to deal with is translating the problem of, I don't know the algorithm yet, but I still need to have something in place, and translating that to a QUBO. And for me, there is no real, I would call it a cookbook yet, like any kind of business problem that you have. How do you now formulate that so that a quantum computer can know it? With the limitations, as you said, there are. And I think the only way that we can get to that point, which variables to take, which approach to take, and so on and so forth, to really drive, okay, you have added value, is to experiment. That's basically what we did at Delaware. We just offered a few days to that customer, and the customer offered a few days to collaborate on that, and we saw, okay, we are onto something. So this approach in this particular case is working. But right now, you don't have anything more than just try to do it as CS4 and use a lot of creativity and imagination to get to that story.
Okay, good, Mark. Making reference, by the way, to a cookbook, as you probably know. Best cooks don't read cookbooks; they just make them. They write them themselves. Okay. So I propose you continue writing your own story. That's the best thing to do. And then we have our last speaker of this morning, Erik Michiels from IBM, and I immediately give the mic to you, Erik.
Thank you very much, Jan. And indeed, so I am technical ambassador at Quantum Technical Ambassador at IBM, and that means that I am, I would say, prepared, certified to present about quantum computing, but also to provide demonstrations, workshops. And when running workshops, I am essentially using Qiskit, Quantum Information Science Kit. And today I would like to focus on what I would call use cases. And I would address several levels of use cases. First of all, I would like to give some overview. What are potential I would say use cases from different perspectives, and then I would like to dive deeper into one of them. Before starting, really, you could say, and you find that on the left-hand side of the screen here, that the main use cases, you could categorize them in three big parts. First of all, there is what we could call simulations of nature, but also of human-made processes. So where there is a kind of, let's say, complexity or uncertainty. The second big chunk is about machine learning and AI. And we already saw a nice example from E.On, the case of the car and the coupled to the grid, for instance, with quantum support vector class I saw. And the final one is more about search and optimization. But then you see the right-hand side of the screen, each of these categories can be applied in multiple industry sectors, and one of them being, of course, energy and utilities, as you can see. Most importantly, perhaps on this slide, is also to tell it is about general purpose quantum computers, meaning gate-based systems that allow to apply multiple types of problems. And that can be interesting because sometimes quantum computational scientists want really to combine multiple types of, let's say, algorithms, not just only optimization, but also machine learning and simulation in one project. And then, of course, it's an advantage to have kind of general purpose system. But let's continue with the next topic, and I would really like to address this because there is a kind of lingua franca, as we could call it, a kind of general language, which is Qiskit, Quantum Information Science Kit, already mentioned by other speakers, which is a software development kit and a runtime environment running on top of Python, and the most popular programming language today. That allows really to access quantum computers. So you can program on multiple levels of abstraction, from very low level of abstraction to relatively high level of abstraction. The nice thing is, and that you see that on the left-hand side, is that you can Qiskit use for multiple types of quantum computing technologies. And at this moment in time, Qiskit is really leading, I would call, the benchmarks. We call bench press is a kind of benchmark approach that checks, let's say, the transpilation and compilation results of the development kits and the speed of executions. You can see that a large part of developers is using Qiskit today, but you see also it's not only open source, it's important to mention, but also a lot of contributions, not only from IBM, but also from other let's say, startups from other parties that are doing quantum computing. You see there are a number, 5,185 projects that are done, even more today, but I will pick out only one of these 5,000. So in the next couple of slides. Also, that allows really to combine multiple types of technology. Not only QPUs, quantum processing units, but also classical processing units and graphical processing units to come to what we call quantum-centric supercomputing. Okay, I will come back on Qiskit later on, but now let's take a look to the use cases really. And the first way to categorize the use cases is start from, let's say, the energy and utility sector itself. So what are different categories of operational processes? On the top left side, you see, for instance, the energy transition part of the operational processes or the initiatives. And one of them is, as you can see, I have multiple examples. I only pick out one of them. That is, how can you better predict the return on investment of your solar and wind farm investments? Because, of course, we all want to transition to the green, more green energy, but what is the return on investment of it? How can you calculate that in a more granular and a more accurate way? That would be a typical example of quantum machine learning, for instance. On the top right side, you find the generation of energy, and you find there things like sensor design. How can you, for instance, improve sensors that you are using in capturing the solar energy? How can you improve that? Then we talk about much more simulations. And the placement of the wind turbines. How can you optimize that? On the bottom of the screen, you find transmission. How can you, it was already discussed also a little bit in the congestion management by Elia. How can you predict, how can you prevent vulnerabilities, and how can you model for them? And the distribution, another example would be, for instance, detecting anomalies in the grid and how to solve them in a quick way. Okay, that are the first way to address it. The second way is to come back on my three big categories I already introduced. And let's start with simulating nature or simulating chemical processes. Think about new battery design. How can you improve your batteries that, of course, are very important also when you see more and more people installing batteries in their houses. So how can you improve that? That means that you have to simulate the chemical reactions that are behind these new batteries. For instance, lithium sulfur batteries. How can you do that? So that their quantum computing can play an important role. Corrosion inhibitor as another example in that first category. We saw all the example of the electricity poles. How can you, for instance, improve these electricity poles so that they are less subject to corrosion? And that would come, for instance, from the world of the airplanes, where we also have the same type of problem. In the middle, you see machine learning and AI. Think about, of course, how to predict failures of certain types of equipments or assets. On the right-hand side, you find workforce deployment, how to optimize the resources, human resources, taking into consideration schedules. And you also find the prosumer problem. And that is the one I'm going to dive into now a little more in more depth. First of all, the prosumer, and the prosumer is, of course, a word that is a combination of producer and consumer of solar energy. We all are becoming prosumers, and that is, of course, a challenge for the energy and utility sector or the energy sector. How can you, let's say, optimize your energy strategy for the production, purchase, and sale of this energy? And this is the business question, but you can, of course, boil that down to a more engineering or a technical question, and then we talk about minimization of a cost function that is referring to a monetary cost, the total energy consumption, or the brown energy consumption, not the green, but the brown energy consumption. So it's an optimization problem that we are addressing here. And already in the previous sessions by José, we saw the MILP, M-I-E-L-P, the mixed integer linear programming problem, excuse me, in which you combine integers and real numbers that you need to optimize. To make a long story short, you can represent this prosumer challenge also as an MIELP problem. It's NP hard, as already discussed in the previous sessions. And there exist, of course, classical approaches, like the cutting plane approach and the branch and bound approach. But they seem not to be sufficient once the problem becomes too large in size and too complex. And there, what we see is there that variational quantum algorithms, VQA, can offer a better alternative. The first thing that we see with these types of algorithms is better scalability, meaning if the size of the problem increases, the computational time and the number of operations will not scale, will not grow exponentially, but will scale much better. So it's an approach to tackle uncertainty. Let me now come back a little bit on this VQA, variational quantum algorithms, and you find that on the next slide, on the left-hand side on the bottom, you see the pattern of such a VQA algorithm. You see an orange and a blue set of quantum instructions. These instructions combine multiple quantum gates. And the orange parts, they are really, let's say, they are used to encode the data, because in quantum computing, and I think also this was addressed by Mark already, one of the challenges is to really convert your, let's say, your classical description, your classical representation into a quantum and qubit representation. So that is what is happening in these orange parts. And then you see the blue parts with a theta parameter. That is a parameter that will be optimized by a classical algorithm, for instance, the Kobila algorithm or the SPSA algorithm. And by using a kind of a set of iterations, we will converge a cost function downward towards zero. And that will then deliver the ultimate right, let's say, circuit, or the right algorithm. This is the general principle. So now let us take a look to the rest of the slide. And I start at the top with the MILP problem. We transfer this into a QBOR problem, already addressed a couple of times today, a quadratic unconstrained binary optimization problem, in which you have embedded the constraints of the MILP problem so that you don't have any constraints anymore. You finish with variables that are binary. You express this as an Ising formulation in which you have values that can take 1 or -1, discrete values. These are transformed, in a Hamiltonian operator. Hamiltonian is describing the energy of the system, and also here we try to find the minimum value, so the minimum eigenvalue and the corresponding eigenvector. And this problem can then be solved with the VQA approach, in which the Zi variables are represented as quantum gates, let's say Z gates. And then you see two other new things, QAOA and recursive QAOA. Let me explain that one. So QAOA is about the quadratic approximate optimization, quantum approximate optimization algorithm. And it is based on the combination of two types of Hamiltonians, meaning that you find a minimum, but you try to avoid a local minimum. You want to find a global minimum by using the mixed Hamiltonian. And this is a kind of approach that you don't only find in, let's say, these types of optimization problems for the energy sector, but you find them also in all types of optimization types of challenges. I am now addressing a kind of, let's say, research that has been done by a team, and they have been using recursive QAOA, meaning they have improved this algorithm by eliminating qubits that are correlated to each other to reduce the size of the problem and improve the, let's say, the efficiency of the calculation. And let me now take a look to the results. Before doing so, saying that given the fact that today our quantum computers are, the moment that this experiment was done, the quantum computers only had a limited number of qubits, and I will address that on the next slide. The problem was a little bit simplified, only with two schedulable loads, L1 and L2, the number of hours of each load only between 2 and 5 hours, with only 5 prices, so a limited number of prices, and with a maximum amount of power that could be only 3 kilowatt. So to make a long story short again here, so some simplifications so that the quantum experiment could be done with this in this situation. And the VQA was used. This is a heuristic algorithm. What we see is that this heuristic algorithm is not the first example in which we see a better performance than, let's say, in a classical analytical approach. The only caveat is that sometimes this convergence, of which I was talking in the previous slide, does not always happen very smoothly. There can be what we call also barren plateaus that make the convergence, let's say, challenging. By the way, if you want to read the complete story, you see on the bottom of the slide on the right-hand side a reference, and I really recommend to read the paper with all explanations. It's a research paper, and I will present now on the next slide the results of this study. First of all, let me take a look to two values, p-ADM and p-best. What does that mean? It's a probability to find an admissible, an acceptable solution, and a probability to find the best solution. On the right-hand side, you see a curve, and you see the red lines. The red lines are referring to the usage of the new recursive QAOA. And you see that the probability to find the best solution is consistently higher than finding the best solution with the classical QAOA. So the recursive QAOA is certainly doing a better job here than the classical QAOA, I would say. And on the right-hand side, even a more interesting result, because there we see the comparison between the quantum approach with the small crosses at the top of the graph and the classical approach using CPlex. CPlex is a software, an optimization software that is running in a classical environment. What do you see there? You see that when you increase the number of binary variables, the required time to get the solution is much more stable for a quantum approach than for a classical approach, indicating the high scalability of the quantum algorithm. So we can expect, if the problem size grows, we are almost sure that the quantum approach is scaling much better. So in other words, the size of the problem can grow and your quantum approach will be able still to tackle the problem even if the size becomes larger. Yeah, that is then a very interesting, let's say, conclusion. Now, to finish my part, I would say that the previous results I showed on the previous slides, excuse me, they have to do with, they were executed on a quantum computer from IBM Q Montreal, as you see on this slide. It is already some generations old because it is using one of the previous QPU technologies. Today in 24 and 24 we are on another type of processor already, the E.On processor, which is already of much higher quality, but still suffering from some noise. As you might have heard and already referred to by Jose, in 29 we will have full fault tolerant quantum computers with full error correction with 200 qubits that are perfect qubits with 100 million of gates. Does it mean that we have to wait for such a long time to do quantum? No, you can already start today, because we expect quantum advantage already next year. So not quantum supremacy, already addressed in one of the questions, but quantum advantage, meaning that the combination of quantum and classical will do a better job than classical only. What is a better job? Meaning your result is more accurate or you get it faster. Yeah. By the way, these technologies are already accessible via the cloud. Some environments are on-premise, but you can already access these, let's say, the E.On processor via the cloud in 25. And then the future will be, as you can see on this roadmap. I could spend much more time on this roadmap. I will not do it, but just one final remark. So you see that the result of this experiment was done on a quantum computer that is already a couple of generations old. Today, the results would even be more promising. Okay, that was a little bit my part of the presentation. Thank you for the attention.
Yeah, very, very interesting, Eric. And also regarding to the roadmap, we have seen an announcement recently, a couple of weeks ago, and it's impressive to see how IBM over the years is following up on the roadmap, following up on the promise, if you want to take it like that. So we are sure that you will reach that milestone in 26. There's another thing that makes me think already all the time is what you explained, is where on one hand, in classical computing, we are spoiled, I would say, with capacity, which is rather cheap and which is not always used in the right way. If you ask me, in times of Gen AI, what you guys, all the four of you show us is that we deal here with scarcity, with something which still is very expensive to use on one hand, but it's also an advantage because it forces us to be super, super creative. And it makes me think, and tell me if I'm wrong, the first program language I learned, apart from BASIC, was assembler. And to program my little calculator, my HP, and yeah, it's a bit like that. You have to deal with little memory and so on, and almost no memory in quantum, and that makes it very spectacular. And that's why I invite everybody who has to do something with programming skills to dive into quantum, and Qiskit is certainly one good way to get ahead, because it's quite easy to use, to be very honest. Yeah, I see there's questions in the Slido.
I think we have time for 2 questions for Eric. I like the first one because we've seen in many presentations speaking about Cubo, we've seen two cases in which we have used annealers, and now we mentioned the QAOA. So could you develop on when you have to use one or the other?
Oh, yeah, I think it is that is perhaps not clear to say. The only thing I could say here is that we have different types of approaches. We have the QBO problem, and you can indeed tackle it with the quantum annealing technology, or with let's say the more gate-based quantum technology. And when you use the gate-based quantum technology, you use the QAOA algorithm. I would not express myself here what is better, what is the leading, but I think both have been experimented, have been tried out, and both work, in my opinion. So perhaps, Mark, you have to add something to that.
The reason why I chosen the annealer part, because that was available with really a lot of qubits. Right now, if you could go to at 3 years ago, at the amount of gate-based qubits, that was very limited, and I could not apply it to the 5,000 nodes that I had to simulate. So that's the reason why I chosen the annealer. There are even use cases, maybe interesting to also put that on the table, use cases where I needed millions of qubits, and that's still, years to go. And then you can go to a quantum-inspired optimization. If you don't really need to have like a second level approach that you have an answer in seconds or minutes, if you can take a day, which is better than having nothing, then you can also go that kind of direction. So that's a third one that I would like to put on the table here.
Yeah, indeed. Another case, so with the QAOA algorithm and the recursive QAOA that I mentioned, it can be applied today, but of course it can also be applied later on when we will have our qubits that are completely error corrected. So
yeah, very good. There's another question specifically on the QAOA. The question is if this can be applied to multiple use cases and not just in the energy and utility sector.
Yes, it can also be applied outside of the sector. As soon as we have an optimization type of problem, it can be applied. It can be an optimization problem in the finance sector. I know, for instance, in the quantum network, we have customers in the financial services sector that are using the QAOA also for their optimization types of problems. And then I talk about portfolio optimization, for instance. So yes, it can be used in other sectors as well, as soon as you do optimization. Yes, sure. Yeah.
Very good. I see there is a lot of interest from the audience, but I think that we have to move on, and then we can keep these questions for the end.
Yeah, that's a good proposal. And even if we cannot answer all questions this morning, what we will do, as I said in the beginning, we'll send out the recording after the session, but we'll also look deeper into the questions, and we'll certainly get back to our audience in written in answering a couple of these questions. So thank you for continuing to ask the question. So far we had two parts: an introduction by Jose on quantum for those who are not that far, a little tutorial. Then Jose took us into the adventure here at Elia, which was a good head start. And then I can only say that he was confirmed in his presentation by the other speakers, all giving their perspective on a use case, a project, on what is possible already. And this is the part, honestly, I like the most, and the part that I think a lot of researchers will also appreciate, because we are fully honest here about what is possible and what is not, or not yet. And that's what the second or third part, I must say, is all about. We have two remaining questions, but for the whole team around the table here. And my first question is, what do you see as limitations today? And it was in one of the questions, I think, as limitations to go industrial with quantum. And maybe because you were the last speaker, Erik, I will first ask the question to you. What do you see as the limitations we still have?
Yes. So indeed, so the main limitation today is that, let's say, the number of high-quality qubits that you can really use in your algorithms and the depth of your circuits due to the noise is not yet where we want it to be, a little bit limited. So you see that a lot of problems have to be a little bit scaled down in order to be able to be processed. And if you scale down the problems, they are probably not production ready anymore. But I have to add to that there are error mitigation and error suppression techniques. And if you master these well. This is about, let's say, programming techniques. You can achieve much more. You can go up to, let's say, more than 100 qubits and more than thousands of gates to do something useful. So that was also why we expect quantum advantage next year already, because you can apply these techniques. Yeah, but it will be probably not, it will be probably niche problems in production that you will be able to tackle, but that is not yet today possible. It will be for the near future. Yeah. Yeah.
But it would be much cooler though than as we saw in one of the presentations. I think it was in Jose's, where some vendors, and I will not give names here, talk about use cases that are completely useless today, to really talk about cases that are useful, even if there are a lot of limitations linked to that. I think it would be good for the belief, certainly when we talk on a decision level with CXOs, it would help them, and I think that's what helps the Elia management also to decide on going on with quantum. Jose, what is your take on that?
Yeah, I would like to add into that yeah, I showed my presentation. Indeed, today we did not manage to use quantum for a very simple congestion management. And there is one reason, which is what Eric mentions, is the qubits are still not perfect today. That's one part. But there is also another part which maybe hard learning, which is you need to relearn to do computer science when you go into quantum. So here with the annealers, we have to reformulate a QUBO. And this, also with Mark's presentation, is not straightforward. There are a lot of choices to be made on how you translate all your variables into a QUBO. If you go into universal quantum, you need to learn again to program. We are all used with classical computing today just to write a Python script, and then it's going to be translated into assembler in this whole process and be run seamlessly to you. It's not the case today with quantum. You need to know what's going on at the hardware level to understand why your QUBO is not working. And obviously for Elia, we cannot today do congestion management with quantum. We are exploring other solutions, such as HPC and reinforcement learning, but this is just a matter of time. We know this is an NP-hard problem, so it's scaling in a way which will become more and more complex. At some moment, we'll hit another ceiling, even with HPC or reinforcement learning, and then we hope that with rapid progress in hardware, that maybe in the coming years we can revisit the use of quantum for congestion management.
Okay, I suppose with the HPC, you mean high performance compute?
Indeed,
classical high performance compute. Did you want to add something to that?
Yes, indeed, the skill development is really important, but there also we'll see an evolution, as Jose mentioned, indeed, so that transformation of your, let's say, classical thinking into the qubit representation, the quantum representation, is a challenge today. But what we see, of course, there are some, let's say, tools are being developed. I think about Qiskit functions, thinking Qiskit add-ons, and also even we see, let's say, generative AI coming up in that space, that you generate code so that quantum computation scientists can focus more on the, let's say, the logical aspect, and that, let's say, the really quantum machine-oriented part is generated. So that is, of course, not yet today possible, but that is that is, of course, going to happen in the near future. But I agree with the skills. You need the right skills today to make something, to do something useful. Okay. I agree completely. Yeah.
Okay, it's very, very honest of both of you to talk about limitations. Suppose that we have less or no limitations. Maybe, Mark, if we look at the future, because you left your presentation with a sort of an open end. You said these are things we didn't look at, and so on. If you could go from here, what would be the future for you? What could be a next step?
Well, for me, it's to stay in the language of cooking, of course. The proof of the pudding is in the eating, as they say in English. Just try it out, what you can already do today, to come back to the limitation part, what is already possible today. There are businesses, and there's more than 5, I must say. There are businesses today that are running quantum computers, quantum annealers, on an hourly, on a 15-minute basis even, and are seriously improving their performance with that. So if you find a solution, and that's maybe very interesting, if you find a solution to that with the already ongoing offerings that there are, it might be a huge leap for your business. Might be. It's always a question. So just by doing some experiments, you can rule that out and learn, oh, maybe you have to come back if this and this and this is announced, that you at least have something to go for. Right now, most businesses have nothing to go for. And I must say, if I start talking to C-levels and really businesses with problems on the floor, usually they have a problem that they worked around it, that they don't know it anymore, that they have that problem, that they don't know that this can still improve, but they just find a way to live with it, but they never thought to be able to do the next step and coming back to that dream that usually occurs. Yeah, but if you could solve this, this and this, and this could become possible, solving a lot of other problems already on the go. So doing those experimental steps is for me the right step to take. You want to do that.
Yes, we sometimes say there are no fast followers in quantum. So yeah, you should even in your company nominate a kind of quantum champion. Perhaps not full time, but if follow it up, invest in it, try to understand it, and yeah.
Yeah, that's about the same advice that we give if we go into conferences or events. I think we do the same. We always say, don't invest heavily. It's not necessary. And by the way, that's what most consultants are saying. They are not saying like the metaverse, you have to jump on quantum with all you have, or like blockchain and so on. I think they all made these mistakes a couple of times. So they are not doing that with quantum. And it is true, if you put some people on the topics, as you said, Eric, Qiskit is an open source product, but there's a lot of open source and free trainings and courses and so on. We always say, go to a conference, and there's tons of conferences organized all over Europe. They are not very expensive. And just to get this first grasp of what quantum could mean for a particular business, you're quite confident, Eric, that I always heard these terms like supremacy and also utility. Can you say something more about the IBM's expectations longer term?
Yes, we, as I said, I already mentioned that in 29 we'll have fully error-corrected quantum computers. And that will, of course, open doors, because then you have 200 fully error-corrected qubits. Yeah, and if you go then back, then you can go back to the quantum information theory. Yeah, you have 2 to the power 200 dimensions that you can represent in your problem, and it will become even higher in the future. Yeah, and with 100 million of gates, yeah, then I would say then, yeah, we cannot predict what will happen then, but quite some problems will be solvable. And in the meantime, I would say by using error mitigation and error correction, you can already do some useful things and already start today. Eh? And now something special that I'm going to say is also there are even quantum machine learning algorithms that like the noise, to say it like that. Eh? So that exploit the noise that have in the current machines. There are examples of these types of algorithms. So you never can tell that the noise will also be useful. Eh? So
yeah. They could take the noise into their advantage.
Yeah,
but then you come into the nature of quantum computing, into the promise of the thing that we really don't understand.
But of course, the goal is to have these, this evolution, we will see what it will bring, but it will bring a lot of these promises that we think about today. So, yeah.
But you also already told me, Jose, that it still requires a lot of research as well. And you stressed on the fact that it's better to start now. Can you say something more about the research part?
Yeah, sure. So what we see today is that when we look at Elia and what we discover in this journey with quantum is that it requires a lot of different skills. So here at Elia, we have very good business expertise. We have very good electrical engineers, and we have very good economists that they are designing the grid of the future and the electricity market of the future. These people, they can come with the problems that they say they are very challenging today. This we don't find a way of solving it. Can you please help? And in that sense, then we need to have mathematicians that can maybe see, I can use a simplex, or I can use this other formulation. We need computer scientists that will say, I see this problem is now it's working, but in a few years, it will not be the case anymore. And what we see that if we want to jump into into quantum, we need this new expertise. We can find mathematicians, we can find computer scientists, but we need the combination of all this together, especially of the quantum expertise. And also something that is surprising when you go to all these conferences is that you hear very often the QUBO, the QAOA, even in other industries, not just in the utilities, but in all these conferences we've seen presentations by E.On, Tenet, also Spanish bank BBVA. They are also investing into quantum, and we talk with them, and they have the same issues, saying we had our QUBO and we put it and it didn't work. Why? We're trying to think why. So rather than having all these different people, like the industry on one side, the academia and the providers, I think that the way forward is maybe to have some consortia. And if we see that we're stuck somewhere, and because at Elia we cannot find someone to do an optimal QUBO formulation, we can maybe go to academics and say, oh, there is this researcher working on that. And in that sense, we were in contact with Fraunhofer Institute, with Jülich, with TNO. So it's there. And in terms of the providers, we have IBM here with us. There are also Fujitsu, there are D-Wave, there are many possibilities. So I think for me, the way forward is to put all this knowledge together.
Mm-hmm. Yeah, I cannot agree more with you. To be honest, the tour I'm doing since more than 1 year now here in Belgium shows that there's a lot of talent, that there's a lot we already have in hand, if I may call it like that, at universities and research centers here in Belgium. You visited a lot of them here, yes. Erik. Sure. There's tons of talents. What we see happening too much today is that this talent, once if they come out of university, they leave the country. So we need a startup community. We need a business around quantum here in Belgium as well, as we see happening in countries around us. What is encouraging for those who don't know is that on a European level, a lot is going on. The European Commission invests a lot in quantum. It supports its countries in the space of quantum computing and communication and sensing a lot in computing through the European flagship initiative. A new flagship initiative update, I should call it, will be announced later this month with a vast investment in quantum. So, and what we also see is due to the geopolitical things happening lately, that NATO recently declared quantum as one of its top 3 technologies for the coming 20 years. So you better start to pay attention, I would say, to the technology. And also here in Belgium, maybe a last thing is our community. I mentioned in the beginning, we set up this community early last year. I first met people like Erik and a couple of others. We were about 10 in the first meetings we had, the first meetups, and today we are a lot. Some are loosely coupled, but we have about 20-30 organizations that really invest in quantum. That's why I'm also so happy that Jose reached out to me with this proposition to do something, because it complies to, I would say, our second goal of the community. Our first goal is to evangelize on quantum, on the possibilities, also on the limitations, on the opportunities from a business perspective, because a lot is already been doing and going on at the university, the academics level, but we look at things from a business use perspective, like Marco also explained in his case. So that's our first goal. The second goal is to get people together, and it would really be a dream to get out of this webinar people coming to us, people we don't even know, and say, hey, if you set up a project, a consortium, like you called it, Jose, I want to be in that consortium. We'll definitely find funding for that. And let's work on these bigger problems that can help us to balance grid or optimize water leakage or other replicable cases in other industries. And then the third thing we are doing as a community is we are making a first draft of what could become a strategy for Belgium, because for those who don't know, quantum, there is a strategy in, I would say, 10 to 12 countries around Europe, also, of course, in Canada, US, Japan, and so on. But in Belgium, we still lack this one vision in terms of federal and regional level of where we want to go in, where do we want to play, where do we want to be at best. But again, as said already, we have a lot of talent everywhere spread around in Belgium, and our plead or our best, I would say, present for today would be that you contact us and that you come and sit around the table with us and see how we can further explore quantum together. This brings me to my end of the presentation of this morning, but I think that we still have some time for questions.
Indeed, I see that it's quite active on the Slido. We have a first question here. If quantum computers require cryogenic temperature, vibration isolation, and ultra-clean environments, how can they ever be operationalized in a distributed energy ecosystem where resilience and decentralization are key?
Yeah, I can take that question. So indeed, if you take superconducting technology like we are using, you need that cryogenic equipment, cryogenic circumstances. Of course, that is, I would say, that is in the data center. So we have 12 quantum computers running in the cloud. They are, of course, in the ideal situation. They are in the cryogenic equipment. So there is, and of course, the stability, no vibration. It's all there. It's equipped to be there. Right? Even if we install in systems on premise, what we also do there, we manage the environment as well. We make sure there are not a lot of vibration, that we bring in the cryogenic equipment, so we create the circumstances to operate correctly. That avoids the problem of let's say the operational potential dangers. No, so we take care of that. That's in our situation.
And maybe to add a bit on that one, it's also like with AI. So when you use AI, you are using huge data centers to train models, and then you deploy somewhere else. So it's not that you put all the processing power somewhere. You are using huge data centers today in classical computation for some specific cases.
Correct. Yeah.
So it shouldn't be the user's problem.
Exactly.
No, it's not. We don't have yet quantum laptops.
No.
Another question?
Yes, this is a very good one. Both examples have nodes connected with edges holding a range of parameters, turning a node edge model into a QUBO model. Yeah, it's something that could be approached to other industries. I've seen that, as I said before, in the bank industry. I think that you also, Mark, you have seen that somewhere else.
Well, I was thinking about this one, nodes and edges. What I had with the water industry was nonlinear combinations of stuff. So it is still edges and nodes, but translating it to a QUBO, you see how much problems I have with that. If you have a QUBO, there's a standard approach to that, or there are standard approaches coming along. Translating your problem, whether it's a graph problem or not, I think that still requires some knowledge about your business process. And I was thinking about logistics also to be able to do a case there. You can easily translate, this is my starting point, this is my ending point, but what are you actually modeling? What is the meaning of all these things? That's actually the important point to be able to translate it towards a QUBO. So it's not really a one-to-one kind of combination of things as far as I know.
Mm-hmm. We do one more question?
Yeah, I think we have some time for more questions. I see here, how involved in quantum are the leading AI companies, Google, OpenAI, etc., and what kind of impact will quantum have on AI?
I can address the second part of the question. There is a kind of, let's say, there is quantum for AI and AI for quantum. Quantum for AI, you could call it quantum machine learning. So you can then run part of the quantum the machine learning algorithm. You can execute parts of it on the quantum processors. And in a hybrid mode today already. And that is what we call quantum machine learning. So that is, let's say, the idea to enhance your machine learning, AI also, that can also involve deep learning and other examples, to improve your AI with quantum computing. The other way around, we also see AI to be used in quantum computing systems, for instance, in the transpilation of the quantum circuits into circuits that are executable. We see reinforcement learning being used. Another thing already addressed, you see also generative AI being used to generate code for quantum. So there is a kind of bidirectional, let's say, virtualization, or how would I call it, or influence of quantum and AI. Of course, the first part of the question, I would not know. Google and yeah, Google I know, but OpenAI is a little bit outside of my expertise.
But isn't there a logic that big tech is betting on AI first? On quantum, they have big deep pockets, as we always say, and they see it as a continuum for CPUs and GPUs and now QPUs, and it's just a next step. What it will bring, I'm sure they don't always know themselves, but they just bet on it and invest in it.
Yeah,
that's a logical step for them.
Yeah, I would like also to have some comment on that. I see three areas where you can have already impact on quantum towards the AI. The first one is the one that I showed, the quantum feature selection. If you have a table of 5,000 columns and a very long one, you can translate that in a Kubo, and within a second you have the solution for that. Sometimes that gives problems if you have that size of a problem. So that's one thing. A second thing, which is very interesting, I think, is QML. If you train a model classically or you train it based on a quantum computer, you need less information if you do it the quantum way of working. That was for us the first attraction point, basically, what we saw happening. So making use of noise and stuff like that reduces the amount of good quality data that you need to be able to same kind of quality of your model. And the third one is basically if within machine learning processes, there is optimization being involved. So if you could also use the quantum speed and correctness and optimal point that you have the quantum promise of the optimization step inside the whole machine learning approach, that could have added value. If, of course, the classical approach is not doing very well, because sometimes quantum is taking a little bit longer than the classical step. So you have to see where you are in that spectrum.
Okay, but if I look at the time, I think it's best we close here. As promised, we'll send out the recording. That's one thing for those who had to leave from time to time, a couple of minutes their desk. And also we look further into the questions from your side. Our question is really reach out to us. Reach out to us through LinkedIn, through mail. You definitely, if you know something about Google search, you'll find us as well. So because that's what we want to do. We want to build, as Jose showed at the end, we want to form a sort of a consortium of companies, organizations from research. It can be students to step in and to see how we can further explore this thing. It's a very, very interesting thing to do. And it really would advance quantum development in Belgium. And to really finish off this morning, I would like to thank you, of course, dear viewers, for staying online for 2 hours. I know it's it's a long take. I thank my guests here around the table, speakers, Giorgio, of course, who was not on site here, Mark, Jose, and Eric. And I especially would like to thank the Elia organization for hosting this event, for preparing this event. And certainly the Elia media and communication teams, they were very patient with us in preparing this session. I really my deepest respect for the way they did that. And with that, we'll close the session, guys.
Thank you very much, Jan.
Thank you very much.